Hello, my name is William Vanden Boger, and with the help of my faculty advisor, Dr. John Shaw, I would like to present my Engineering Honors Capstone project, Synthetic Dry Adhesives for Human Scaled Climbing of Vertical Surfaces. The goals of my project started in three stages. First, I wanted to demonstrate the adhesive capabilities of specialized compliant composite materials. Second, I wanted to show that human climbing using these dry adhesives was feasible. Third, I wanted to demonstrate human climbing of vertical surfaces using these dry adhesives. Now, a bit of background. This whole idea is based around the biology of geckos. Geckos have the unique ability to scale perfectly vertical walls. This is enabled through microstructures called setae found on the gecko's toe pad. These microscopic hairs serve to maximize the molecular contact area with the surface, multiplying the usually weak van der Waals attraction between molecules into very high forces. If you've ever taken a chemistry class, yes, I am talking about the same van der Waals attraction that is considered a weak secondary bond. That's the same force that allows geckos to scale vertical surfaces, and the same force that I'm proposing can be used for humans to scale vertical surfaces. Many different approaches toward mimicking this van der Waals adhesion have been undertaken, primarily by trying to replicate the setae, the morphological feature. Ali Dinajwala at the University of Akron pioneered the use of carbon nanotubes as synthetic setae, which seems simple enough. Both the carbon nanotubes and synthetic setae are microscopic and fibrillar in nature. This technology was able to create a 16 square millimeter adhesive pad that had a shear stress capacity of 200 kilopascals. Metin Siti at Carnegie Mellon University developed polyurethane synthetic setae molded in microscopically detailed molds that were created with lithography, leading to a 300 square millimeter adhesive pad that had a shear stress capacity of 40 kilopascals. Mark Kutkoski at Stanford University developed silicone microwedges, which patterned a 650 square millimeter adhesive pad that had a shear stress capacity of 80 kilopascals. It is important to note that the shear stress capacity is how much force the adhesive is holding per unit area. Ideally, the maximum adhesive force, or the force capacity, scales linearly with the area, much like the maximum tensile force would increase with the cross-sectional area of a rod. That is to say, ideally, the shear stress capacity would be constant, regardless of area. However, it's clear from these very similar approaches that the two adhesive pads with the largest area actually have the smallest shear stress capacity. This would indicate that as you add more area to the pad, the area you add helps increase the force capacity less and less as you add area, and so the shear stress capacity falls. This is known as inefficient scaling. Now let's take a look at a different approach, one that is much more accessible because it does not require microstructures, which are difficult to fabricate. This approach was pioneered by Al Crosby and Duncan Ershik at UMass Amherst. They utilized compliant composites consisting of a compliant matrix reinforced by stiff fibers. The compliant matrix serves to increase the compliance perpendicular to the surface, which essentially helps the adhesive pad conform to surfaces, acting just as the setae would to maximize the molecular contact area. The stiff fibers serve to decrease the compliance or increase the stiffness parallel to the surface to give the strength that the adhesive needs to support large loads. This is much similar to the way geckos have a stiff tendon woven directly from their setae into their skeleton. From this approach, the researchers also developed a scaling theory that the adhesive's critical load, the force capacity, will scale proportionally with the quantity of the square root of the area divided by the compliance, where the compliance in this case is measured in shear, parallel to the surface. A third parameter in the scaling theory, G sub c, is a property of the interface between the adhesive and the adherent. It was found in the research done at UMass Amherst that the highest performing adhesive was comprised of a polyurethane matrix with a hardness of 60 short A and carbon fibers reinforcing it. Additionally, it was shown that adding a rigid tendon to the center of the adhesive pad so that all of the adhesive force is transferred through it increases the force capacity at loading angles other than 0 degrees to the surface. So I implemented this in my design as well. I had high hopes for this approach, as research from UMass Amherst showed an unprecedented shear stress capacity of around 300 kilopascals for an adhesive pad with an area as high as 10,000 square millimeters. Better performance than any of the other approaches by a wide margin, demonstrating that this approach scales much more efficiently than all the others. For my experiments, I first had to fabricate the adhesives by embedding the carbon fiber in a polyurethane matrix. I used 3D printed molds to control the size and shape, and a borosilicate glass surface on which to mold the smooth adhesive surface. I added my center loaded tendon that prevents peeling at other loading angles as a second layer of carbon fiber bonded partially within the polyurethane matrix. But my approach was not perfect by a long shot. My fabrication method produced a lot of defects on the adhesive surface, and I was only able to get one high-quality adhesive about one time in 20 tries. But once I had this high quality adhesive, I was able to perform testing on its ability. Using a custom built testing setup with a polycarbonate plate as the adherent surface that is allowed to rotate about an axis so that I could test different loading angles, I performed simple force versus extension tests on the adhesive, where the Instron instrument increases the displacement on its anchor while measuring the resulting force using a load cell. The raw data from these tests all revealed two things: the force capacity, which is the maximum force measured before failure, and the compliance, which is the reciprocal of the slope of the linear region, i.e. the reciprocal of the stiffness. My pilot testing with a smaller adhesive pad led me to hypothesize that three 3-inch wide by 12-inch long adhesive pads holding a load in parallel could be enough to hold my weight of around 756.2 newtons, meaning that each pad would have to hold around 252.2 newtons. All tests of a good quality adhesive surpass this measure, with the minimum safety factor being 1.16. Additionally, after 8 cycles of loading, removal of the adhesive, cleaning of both surfaces, and replacement of the adhesive showed no significant decrease in force capacity, something that could not be achieved with standard glue-covered wet adhesives like tape. So this is promising. I do want to point out that my testing setup was not perfect either. There were some instances where the clamp failed to hold onto the polyurethane surfaces of the tendons, and some instances where the limit of the load cell was reached at about 450 newtons, or about 100 pounds, before the adhesive fully peeled. There was also some tests where both of these things happened, so the experimental setup could be improved greatly. My initial design for the climbing paddle used 4 tendons placed periodically throughout the height of the pad in order to keep the pad oriented about parallel to the climbing paddle, which would aid in adhesive placement. So my next test was to examine how the force capacity changes when you're loading different tendons. I found that loading the tendon closest to the center led to the highest critical load of about 371 newtons, while loading the tendon highest on the adhesive led to a significantly lower critical load of about 30 newtons, presumably because the adhesive begins to peel. Only the tendon closest to the center had a critical load above the 252.2 newton requirement. With the highest and loading being the weakest points, I elected to eliminate those in my climbing paddle design, instead only relying on 2 tendons closest to the center. However, the uppermost tendon is still a weak point, but we'll get back to that later. My results from my examination of the effect of loading angle with respect to the surface seemed to agree with the results obtained by UMass Amherst. My experiment showed a significant decrease in force capacity as the loading angle increased. My final investigation was into whether my experiments supported the scaling theory developed by Crosby and Urshik. Throughout all of my experiments where the adhesive was the thing to fail, regardless of loading angle or pad area or pad quality, a somewhat linear relationship can be seen between the critical load, the force capacity, and the quantity of the square root of the area divided by the compliance. However, the best fit slope that I obtained is somewhat higher than that obtained by Crosby and Urshik. However, there's a potential explanation for this. I used polycarbonate as my loading surface, and they used glass. Polycarbonate is a significantly more compliant material, thus the compliance that I have measured is actually higher than the actual compliance of the adhesive. So the horizontal coordinates on this quantity of square root of the area over the compliance are actually smaller than they should be were I actually measuring the compliance of the adhesive. So the slope should be lower than it appears here. However, I haven't done anything to account for this, so this is just a hypothesis. Now in my experiments, I was able to create adhesives that only had a shear stress capacity of about 17 kilopascals with a pad area of about 23,000 square millimeters, a much lower performance than the adhesives from UMass Amherst and all of the other approaches for that matter. So there must be something fundamentally wrong with the way I have made them. Now on to the last part of this project, human climbing. While conducting the aforementioned tests, I was designing a climbing paddle that would serve as a means for humans to scale vertical walls made of smooth surfaces like glass or polished stone. My end design consisted of 3 adhesive pads, each with 2 tendons, and 6 tendons are rigidly attached via clamp to an aluminum paddle that has a handle oriented normally toward the top. I made many assumptions during the design process. Number 1, the 3 adhesive pads will hold the load perfectly in parallel, with each sharing an equal load of about 251.2 newtons, as stated earlier. Second assumption, the pads are loaded each exactly in the same manner in which they were loaded during testing. And number 3, all of the adhesive pads used in the paddle are of high quality. Now, these assumptions don't hold, which is something I found after fabricating my climbing paddle. Firstly, when loading the climbing paddle from the handle at the top, a tipping moment is created about the bottom of the paddle, which causes the top tendon to be loaded more than the bottom tendon. And as we saw before, the top tendon is a weak point that cannot support the required load. Additionally, the tipping means that the tendons are loaded more perpendicularly than parallel to the surface, something that also reduces the force capacity significantly. I also have no reason to believe that the pads are acting perfectly in parallel, which would mean all tendons are in the same amount of tension. The way I have it set up, with one clamp for each tendon, all tendons would have to be the exact same length, which is very, very hard to accomplish. Thus, it's likely that one tendon is loaded more than all of the others. Possibly that one tendon is holding all of the load, which my experiments suggest would not support the weight of a human being. All of these oversights culminate in a climbing paddle that can hold at least about 50 newtons or 10 pounds, but certainly not my weight. So what can be done about this? In addressing the tipping moment, a foothold could be added, attached by a long cable to the climbing paddle, and this effectively eliminates the tipping moment altogether and ensures that the climbing paddle is operated almost perfectly in shear. In addressing the issue of parallel loading, a mechanism could be added to ensure that all of the tendons are supporting the same amount of tension. Now, this is similar to how a horse-drawn carriage must do the same with multiple animals. Now, what about my third assumption, that all adhesive pads are of high quality? As I said before, I only had one good quality adhesive after about 20 tries to fabricate one. Now, this adhesive is the one that I used in these tests, but not the one that I used in these ones. These tests clearly show loading the center tendon gives a force capacity comparable to the good quality adhesive. Now, the adhesive pad used in these tests was this one, which clearly has many defects. It could be that the defects don't matter as much as I originally thought. So what is wrong with my adhesives? Well, I've shown that my adhesive force capacities follow the same form of scaling theory that was developed by UMass Amherst. And even if my differing slope is to be believed, it would suggest that it scales even better than anticipated. Now, as the adhesive force capacity is supposed to scale with the quantity of the square root of the area over the compliance, and my area is of a similar magnitude to those produced by UMass Amherst, then my compliance must be too high. I don't know why, but it is my opinion that that would be the place to start in trying to improve the adhesive performance. Thank you all for watching this presentation. Now I am going to address 3 common questions. Number 1, how did I get involved in this project? Now, I was the one who decided to do this project. It's been something I've been interested in investigating for a long time. I brought it to the honors program staff and to Professor Shaw, who were gracious enough to help me develop it. Number 2, what hurdles were most difficult or least anticipated? Certainly the fabrication of the adhesives was something that I did not anticipate being as hard as it was. It took me many times to figure it out, and even now there are things I'd like to improve. Number 3, what other paths could I have explored, or could other students or teams explore in the future of this project? One thing I would have liked to look at is the effect of different adherent materials on the performance. Things like testing the adhesive with glass or drywall or metal, in addition to polycarbonate. With that, I would like to thank Rachel Armstrong and Jason McCormick and all the other honor staff, but it was Rachel and Jason who really helped me get started on this project. And I would also like to thank Professor John Shaw for advising me on the technical aspects of this project, and his student Mohammed Kazemi for helping me develop my testing procedures. I would also like to thank John, Charlie, and all of the staff of the ME Machine Shop who water jetted the parts for my climbing apparatus. Even if it didn't work, it was nice to see my design realized. And I would like to thank the Wilson Center staff, as that's where I machined many of these parts. Thank you all for watching. Here are my references for my research.